Hello everyone, welcome to Digital Electronics lecture series. This is lecture number 13 and we will be continuing with Boolean algebra. We have done some laws. Now today we will be doing this duality theorem now, starting with duality theorem. So what does this duality theorem states? It states that starting from a particular Boolean relation, any other Boolean relation can be obtained, and we can do this by the following way. So if we have a Boolean relation, we can get any other Boolean relation by using these three steps. The first step is replace OR by AND. So if the relation contains OR, we have to replace by AND. And second, replace AND by OR. So if it contains AND, replace it by OR. So OR by AND by OR. And replace 0 by 1 and 1 by 0. So these three steps must be followed. Let us see one example. Suppose we have a relation. For example, if we have this one, we will take a or 1 equals 1. This is one of the relation. Now what is the dual? Okay, I'll just write dual of this. So for getting the dual of this, I write a as it is. So what the rule says, a, then this plus means or, so or should be replaced by and, so this is dot, and 1 by 0, and again this 1 by 0. So this is one relation, we got another relation. Okay, so this is how we get the dual. Now let us take another example here itself. So if we have like let us take a or 0 equals a. So the dual of this can be easily found. So a as it is, so instead of this or plus sign we put and, instead of 0 we put 1, and we get this is equal to a. So this is the dual. So this is what the duality theorem says. Now next is perfect induction method. This method is used to check the validity of a Boolean expression. Okay, so suppose if we want to verify relation, we can use this perfect induction method to check the validity of that equation. Now for example, if we want to prove this relation a or b bar, then a bar or b a bar, sorry. So suppose we have to prove this relation. This is equal to, suppose we can take this equal to 0. Okay, we have to prove this, that this entire thing is equal to 0. So how to prove? By using the method of perfect induction. So for now here we have two variables a and b. Okay, there is no other variable, so there are two variables, so we have to make we take 4 combinations. So we take, first of all, what are the 4 combinations are? The 4 combinations are, we can take I will just write the 4 combinations here. So like make a truth table. I'll just make a truth table and verify the truth table. So I have a, b, and here I will get the output y. So first combination is 0 0, then 0 1, then 1 0, and then 1 1. So we will verify each and every combination here itself and put this for each combination. For each combination we check this. So the first case, the first one 0 0, the first, we will check this one. Okay, so a equal to 0, b equal to 0. This is the first one. So when a equal to 0, so I'll just substitute this one. So this is 0 or 0, then 0, because this is b bar, it becomes 1. Then this a bar, so here a bar means this becomes 1, this becomes 0, then this becomes 1 or 1. So this is equal to this 0. Okay, this is, sorry, I will just, now this actually, here we have AND, there is nothing, it is AND. So this is 0, this is 1, this is 1, and this is 1. So here we have 0 and 1 and 1, and that becomes 0, because any input is 0 for an AND gate, it becomes 0. So 0 and 0 and 0 and 1 and 1 is 0, so this becomes 0. This is 0. Now let's take the second one. Second, it says that we have to take a equal to 0, b equal to 1. So for this combination, this 0 or 1, then here 0 or 0, then 1 or 0, and finally 1 or 0. So here we see this is 1 dot 1 dot, sorry, this is 0, second is 0, this is 0, this is 1, and this is 1. So again, one input is 0, this becomes 0, so here we get 0 here. Okay, then we see the third case. Even in the third case we will get 0. You can check it. Even for the third case, a is 1, b is 0. So we have here 1 or 0, then 1 or 1, then 0 or 0, and 1, sorry, 0 or 1. So this becomes 1 dot 1 dot 0 dot 1. So this is again 0, so we get this is 0. Okay. And then finally number 4 is this is the fourth one. Both are 1 1. So then if we put 1 1, so 1 or 1, then 1 or 0, 0 or 1, and finally 0 or 0. So this is 1 dot, this is 1, this is 1, and this is 0. So again we get this is equal to 0. So here we see all the outputs, all the combination output is 0. So this is, we have verified. This is how we verified. This is the verification. So this is the method of perfect induction. So we use all the combinations, and finally we get output. We can show the output is 0 by this method. Now next term is what is the meaning of a positive logic and a negative logic system. So in positive logic system, what we have is logic 0. It is 0 volt. Okay, because we have to give some voltage to show what is 0 and what is logic 1. So then, but logic 1 is 5 volt. So a low voltage means logic 0, high voltage means logic 1. So this is what positive logic is. This is regarding the positive logic, which is the normal behavior. Okay, then we also have a negative logic. So in negative logic, logic 0 is 5 volt and logic 1 is 0 volt. So this is negative logic. So here high voltage means 0 logic, and low voltage means high logic. So let us see this one with one example. Suppose we have an AND gate. Now how to draw the truth table of an AND gate using a positive logic and negative logic. So this is Y. So I'll just write output Y. Here plus sign means it is a positive logic, and here I will draw the Y minus, showing it as a negative logic. So I am doing the AND operation. So with two inputs, 4 combinations, 0 0 0 1 1 0 1 1. So for positive logic, it will show the normal behavior. 0 0 is 0, 0 1 is 0, 1 0 is 0, and 1 1 is 1. But for negative logic, we have this 0 means here it will become 1, this will become 1, this will become 1, and this will become 0. So this is the AND output for negative logic, and this AND output for positive logic. Generally, in most of the cases, general cases, we always use positive logic unless and until it is stated that it is a negative logic. So generally this is what we use. Now we'll see how to use Boolean algebra to solve the Boolean expressions. So here prove the following using Boolean algebra. We'll see the first problem. So if we are given like you to prove this, and A B C or A B bar equal to A. So we have to prove this relation AB or ABC or AB bar equal to A. So we take the left hand side. How to prove this? First we take LHS, left hand side. So LHS is AB or ABC or AB bar. So here what we see in this case, we will try to reduce as much as possible. So here we see this is AB and here AB, both are common. We can take AB common in both the cases. So in both these terms, so if we take AB common, what we are left here, we will get 1 and here with or C. Now we know 1 or C is equal to 1. So from the laws of Boolean algebra we know this, A or 1 is 1. So same way C or 1 is also 1. So what we have here is now this is equal to A, B, and here we have 1 A, B bar. 1 into AB is of course AB. This is equal to AB. This is equal to AB and A, B bar. Now in this both the cases A is, we can take A common. So if we take A common, we are left with B, B bar. Now again we have this rule. We have seen this rule previously. A or A bar equal to 1. So this also becomes this one. This becomes 1 equal to 1. So what we get is, what we get here is A into 1, and A into 1 is A, which is equal to RHS. Okay, we can see here we have to prove this is equal to A. Okay, so this has been proved that this is indeed equal to A. So we can write hence proved. So this now we prove. Now let us take another example. So we have to prove this A or A bar and B equal to A or B. So as usual we take the left hand side. So left hand side is A or A bar B. Then what we do is this particular A can be written as A or 1, A and 1. It will be same one and the same thing, because this A is A and 1, the same. Then next what we do, we write this one actually as 1 or B, because 1 or B is 1. So we can replace this, we can write this. We open the brackets now. So if we open the brackets, what we get is A and 1, A and B, and here this one. Now next A and 1 is equal to A. So here we have A and 1 is A. Now here in this case B is common, so we can take B common, and then we are left with A bar. Okay, so we are left with this here. Okay, and this is, so we are left with this. Now next what we see, sorry, this is not B, this is not sorry. So if you take B common, what we have is a bar. So here we have a and here we have a bar, which are common. Now we know this that a or a bar is always equal to 1, so this becomes 1. So what we get is a or b, sorry, this is a or b, and this is 1 because of this. Then finally this b and 1 is always b, so we get this. Okay. So finally we get is what we want, which is equal to RHS. Hence it is proved. Okay. So this is what we get, hence proved. So I proved it using Boolean algebra. So this is what we want. You can see this. This is what we want. A or a bar dot b is a or b. So this is what we get. We started with this and we got this. Now next we do the simplification of some Boolean expressions. So now let us start with an example. Suppose we have this first example. We have to simplify this expression, which is given as a or b bar or ab. Then here we have a or b bar, and here we have a bar b. So we need to simplify this. So we can directly write equal to, there is no LHS, no RHS. We have to simplify this expression. So the first step is we write this one, the first one as it is, and we can take this particular, we can this multiply this in, we can take this bracket, we can multiply this to brackets. So first of all we multiply this a with this one. So what we get is a, then from this side we have a bar b. Okay, then next what we do is we multiply this particular b, this b with this. Okay. So what we have is b bar, a bar and b. Then what we get next is, here you can see in this particular expression, here we have a bar. So a and a bar is always 0 and 0, so 0 dot b, and here we have this is b bar and b, both are in the same particular terms. Okay, so b and b bar is also 0, so 0 dot or and a bar. Then what we have next is, this is a or b bar or a b. Now here 0 and b is 0 and 0 and a bar is also 0. Next is a or b bar or a b. Now 0 or 0 is again 0, so we get this as 0. So finally what we see here is this dot 0, so this entire expression dot 0, so we know a dot 0 is 0, so also this is also, this ending with 0 will make this as 0, so this is 0, so final answer is 0. So we have simplified this to 0. Now next problem, this we have to simplify this expression. Okay. So this is the expression. So what we do, we take b common here. So if we take b common, we are left with a or a bar. Okay. You can see we have taken b common here, and here we can take b bar as common. This b bar is common here. Okay. So and here we take b bar common, so we are left with a or a bar. Now we know this a bar is 1, here also a bar is 1, so we are left with b 1 and b bar 1. Now 1 into b, 1 a B and 1 is B bar and 1 is also B bar. So this B or B bar, but B bar is 1. So the answer final one is 1. So this is how we simplify this. Now we have to simplify this expression. The whole bar is there. So we solve the inner things first. This one. So here what we see here, AB and here also AB is common. So we don't directly apply De Morgan's law. We try to simplify as much as possible. So if I take A and B common, I get here 1 and here I get C. Okay, I can make 2 brackets here. Then A, B bar, C. So 1 or C is 1. So what we are left is 1 or C is 1. So I just get here A, B dot 1 and this is A, B bar, C. Okay. So AB, see this should come in bracket. This AB is actually bracket. So AB and 1 is again AB. So we are left with this, the whole, then AB, and here we have A, B bar, C. Now we can just open up the bracket because this is directly ANDing, so it is straightforward. So what we are left with? We are left with this literals A, B, when here A, B bar, C. So here in this expression what we observe, in any ANDing, whenever we are ANDing and we have one term and the complemented of here itself, so this B bar, this makes this 0. Okay, so what we are left with, 0 dot A, and again A is A and C. So 0 dot means, 0 means it will make entire expression as 0. This it will make entire as 0 because this is AND operation, and in ANDing even if a single input is 0, output becomes 0. So this is 0, complement of 0, but complement of 0 is 1. So answer is 1. So that's all for this session. Thanks for watching.